Good morning, everyone. Today we're going to go on to section 7.5. Our objective is to solve exponential and logarithmic equations. So we'll put into practice everything you have learned in section 7.1 through 7.4. Okay, after all, what would algebra be? Algebra or algebra 2 be if we didn't have to solve equations? And so the only way we've been able to solve equations is by using decimals. So to recall, if you had a function like f of t is equal to 20 times 2 raised to the t, and then if the question had asked, okay, how long will it take, hours, days, or minutes, for f of t to be equal to like 1,000, you would have keyed in your function in decimals. Y is equal to 20 times 2 raised to the x, and then you would have looked at your graph to see when y was equal to 1,000, and then that would have given you the value for t, or you would have used the table. Okay, today we'll actually learn how to solve for that. So here, how are we going to solve for exponential and log equations? Well, let's say this here. An exponential equation is an equation containing one or more expressions that have a variable as an exponent. To solve for exponential equations, try writing them so that the bases are all the same. So for example, if the b raised to the x is equal to b raised to the y, then we can say with certainty that x is equal to y, provided that b does not equal 0 or 1. So we say try and find a common base. Try and find a common base. So let's look at this example. Here I have 3 raised to 2x equals 27. What value of x makes that true? Well, I can seek out a common base. I recognize 27 as base 3 raised to the third. So now I have 3 raised to 2x is equal to 3 to the third. My bases are the same now. My bases are the same, so I could just set the exponents equal to each other. 2x is equal to 3. 2x equals 3. X is equal to 1/2. Solved. Okay, so we say find a common base. Let's look at another example. Here, solve and check. Again, notice here, I have 9 as one base and 27 as another base. I recognize that I can write 9 and 27 base 3. Now 9 base 3 is 3 squared, and 27 base 3 is 3 to the third. Okay, so I have found a common base. All we have left to do now is to distribute the exponents, or multiply the exponents. So here I have 2 times 8 minus x, and that will be 16 minus 2x. And then I have 3 times x minus 3. So that's 3 times x minus 3, and that will be 3x minus 9. So I have my exponents then. 16 minus 2x is equal to 3x minus 9. My bases are the same. So I can set 16 minus 2x is equal to 3x minus 9. I solve, I get x is equal to 5. Let's look at some more examples. Here I have 1/2 raised to the x and 4 raised to the x minus 2. I recognize that I can find a common base for 1/2 and 4, and that is 2. 1/2 base 2 is 2 raised to the minus 1, and then we're going to raise that to the x. And then 4 base 2 is 2 squared, and then we'll raise that to the x minus 2. So when I distribute exponents, negative 1 times x, that's going to be 2 raised to negative x equals 2. And then I have to 2 times x minus 2, that will be 2x minus 4. The bases are the same now. I can set the exponents equal to each other. So I have negative x equals 2x minus 4, And then that will be if I add x and add 4, so that would be 4 equals 3x. And so then x will equal 4/3. Add 4 and add x to both sides. Okay, let's look at another one. Here I have 1 over 125 raised to 3x minus 4 equals 125. Again, I recognize I can find a common base. My common base would be 5. So 1 over 25 would be 5 raised to the negative 3. And then we'll raise that to 3x minus 4 equals, and 125 base 5 is 5 to the third. So now I distribute my exponents. So negative 3 times 3x minus 4, that would be negative 9x plus 12. So this would be 5 raised to negative 9x plus 12 equals 5 to the third. My bases are the same, so I can set the exponents equal to each other. So I have negative 9x plus 12 equals 3. And then if I subtract 12, I get negative 9x equals negative 9. Divide by negative 9, and I'll get x is equal to 1. Solved. So again, one way we can solve exponential equations is to find a common base. And you start to see why it's so important to be able to work with negative exponents. Because I had to convert 1 over 25 as 5 raised to the minus 3. That's important to recognize that. So find a common base. Now, the other way in which we can solve equations is by using inverse properties, but then we'll see, I'll show you that using inverse properties, also we could use common log. We could take the common log of both sides. Okay, so the other way, we can use inverse properties, or we can take the common log of both sides. So I'll give you an example of what I mean here. So let's say here I have 4 raised to the x minus 1 equals 5. I can never find a common base for 4 and 5. I just couldn't do that. Okay, but what I could do is I could use inverse properties. And specifically, I will be using this one there. Okay, because I have base 4, I'm working with base 4, I'll just take log base 4 of both sides. Okay. Well, what does that do? Well, using inverse properties, log base 4 of 4 raised to the x minus 1, that just equals x minus 1. Equals log base 4 of 5. But now I can use change of base and change that to base 10. And so I'll have x minus 1 equals common log, because I'm changing it to base 10, over common log of 4. And then finally add 1 to both sides, and I'll get x is equal to common log of 5 over the common log of 4 plus 1. And that would be my answer. So notice how did I go about solving that? Well, I used inverse properties. I recognized that I had the exponent was 4. So I took log base 4 of both sides. And this resulted in me having to use change of base using base 10. So now, the other way in which you can approach that is just take the common log of both sides. You begin by taking the common log of both sides. So I'll show you the example that the textbook gives. So again, I have the same problem. 4 raised to the x minus 1 is equal to 5. So rather than taking log base 4 of both sides, I just take the common log of both sides. But now I have to remember to use the power property. I have to bring that x minus 1 down. So now I have x minus 1 times log of base 10 of 4 equals log base 10 of 5. And then we divide by log base 10 of 4. So that gives me x minus 1 equals log base 10 of 5 divided by log base 10 of 4. And then I add 1 to both sides. But I still got the same answer. Now, why does immediately taking common log of both sides works? Well, because in the end, when I took log base 4 of both sides, I end up employing or having to take the common log of both sides. And so the other way is just to start with the common log. Take the common log of both sides. You get to the same answer. And then we could check that with the calculator. So let's see here. So how would you do that? So common log of, so that would be the common log of, what did we have? 5. Common log of 5 divided by the common log of 4. And then answer, and then plus 1. And that's 2.1609. 2.161. Okay, so a couple more of these examples. And again, first I'll use inverse properties, and then I'll show you using common logs. But either one is going to get you the same spot. Here I see I have base 7 and then base 21. So there's no way I can find a common base. All right, so what I do, because I have base 7, I'll take log base 7 of both sides. Okay, but then here's inverse property. That cancels out log base 7 of 7 raised to the minus x. That's just equal to negative x. And then I'll immediately convert this to common logs. So this is going to be the common log of 21 divided by the common log of 7. And then finally I multiply both sides by negative. And that's my final answer. Which, if you wanted to evaluate, let's see here. So that would be log of 21 divided by the common log of 7. And then the answer would be negative. So let me just make sure that was 21 divided by 7. Yeah, log 21. And then so negative 1.565. So approximately negative 1.565. Okay, so let's look at some. And then the example that they give is they're taking the common log of both sides. So notice here, I took log base 7 of both sides because I'm using inverse properties. But you could just as well take the common log of both sides. But then you have to remember to bring that negative x down like they did there, and then divide by log base 10 of 7. You get the same answer. Okay, so here, let's take a look at a couple more. Okay, so here I have 1/2 raised to the x minus 3 is equal to 7. Again, you can take the common log of both sides. I'll just go ahead and take log base 1/2 of both sides. Okay, so again, I like using inverse properties. Log base 1/2 of 1/2 raised to the x minus 3 equals log base 1/2 of 7. Okay, so again, this is inverse properties. That cancels out. I get x minus 3. And then I'll immediately convert this to common logs. So this would be common log of 7 divided by the common log of 1/2. And then I'll add 3. So my answer will be common log of 7 divided by the common log of 1/2, and then plus 3. So that would be my final answer. And then you could evaluate that with your calculator. Although on a quiz or test, I just look for this. Okay, showing me that you know how to use a calculator is trivial. You don't get much points for that. So showing me the process, though, of how you got from here to there, well, that's the important part. Algebra is a process of using simple arithmetic to solve for unknown variables, although some of you probably won't find this too simple. But it's a process. The process is more important than the final answer. Let's look at the next one. So here again, I notice I have a base 1/4 and base 9. There's no way I can find a common base. So I'll just take, and again, I could have taken the common log of both sides for the previous example. I just use inverse properties. So here again, I have base 1/4 and 9. So I can't find a common base. So I'll take log base 1/4 of both sides. Of 9. So log base 1/4 of 1/4 raised to 2x plus 1, but that's just 2x plus 1 equals, and now I'll convert this to common logs. Change of base using common logs. So this will be common log of 9 divided by the common log of 1/4. So what I have to do first, I have to subtract 1, so I'll have 2x equals the common log of 9 divided by the common log of 1/4 minus 1, because I subtracted 1. And then finally I would divide everything by 2. Common log of 1/4 minus 1, then divide everything by 2. Or multiply by half. So that would be the answer. So let me do that. Okay, so log 9 divided. So that would be common log of 9 divided by the common log of 0.25, because that's 1/4. Enter. Then I would subtract 1. And then what else did I do? Subtract 1, and then I would divide by 2. And that would be negative 1.292 approximately. I shouldn't say equal, approximately. Let me make sure I have the right answer. Yeah, negative 1.292. All right, so there. And so again, on the test, I would be looking for this answer. I need to see how you got from there, from the beginning to the end. And again, I could have used a common log of both sides as well. All right, so here, let's go back up to this. So suppose the bacteria culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1,000? Okay. So before today, the only way we would be able to answer that is to use decimals. So it doubles in size. So I'll just say the initial amount is 1, and then it doubles in size. So my multiplier is 2 raised to the t. So we want to know when f of t. Well, f of t is 1,000,000. So we want to know how long it's going to take for the number of bacteria to exceed 1,000,000. So equals 2 raised to the t. So again, the only way we would have been able to answer this before is to graph that using decimals, and then using our table, find out the value of t. where we got y is equal to 1,000,000. Now we can actually solve for that. All right, so again here I notice I have base 2. Base 2. So what I'm going to do, I'm just going to take log base 2 of both sides. So log base 2 of 1,000,000 equals log base 2 of 2 raised to t. Well, again, this just cancels out. And now I have the common log of 1,000,000 divided by the common log of 2 equals t. Common log of 1,000,000 is 6. So that's 6 divided by log base 10 of 2 equals t. So if I go out here, so 6 divided by the common log of 2, it's about 19.93 years. Okay, so approximately 19.93 years equals t. So as long as t is greater than 19.93 hours, I'm sorry, how many hours will it take for the number of, so as long as t is greater than 19.93 hours, then the number of bacteria will exceed 1,000,000. Okay, the other way I could have used common logs right off the bat. So we had 1,000,000, and maybe this where using common logs would have, I could have taken a common log of both sides. So the common log of 1,000,000 equals the common log of 2 raised to the t. But then I'd have to remember to bring the t down, because using power property. So t common log of 2. Common log of 1,000,000 is 6. And then divided by common log of 2. But you see, we get right back we get the same answer. So we would get t then is equal to what I had before, is equal to 6 divided by the common log of 2. All right, so we looked at 2 ways to solve exponential and log equations here.